Electric power. I like this picture of the Garfield, right, making some voodoo stuff. Okay, so let's get naturally to the idea of electric power. Let me ask you this philosophical question, physical philosophical question. Why do we use electric energy all the time? Why not, I don't know, thermal energy or nuclear energy? There's so many different forms of energy, right? But still, we use electric energy most of the time. And now there are goals to use electric energy almost everywhere, right? Good goal, right? But anyway, so why is electric energy so damn useful? There are two reasons. First of all, it's easier, significantly easier, to transport it over long distances, right? Since we switched, since Tesla won that AC/DC war, right? You remember at the beginning of 20th century with Edison, right? Okay, on one side it was Tesla with Westinghouse, right, as a supporter, financial support. On the other side, it was Edison with J.P. Morgan, right? So there was a big battle, right? Who is going to get all the contracts, right? So which approach is better, AC or DC? It was a cruel war, right? You can watch documentaries, right? But of course, eventually AC won, right? And one of the reasons because it's easier to transport energy over long thousands of kilometers, right, with significantly smaller losses. But if you try to use DC current, you will have to build lots of power stations. Like even now, if you go to the north end in Boston, right, there's one building, it's sort of red brick building, right, and there's a sign. So in this building, Edison used to have his power station. There are lots of power stations throughout Boston because lots of losses, and as a result, you have to build them a lot, right? Because lots of losses. But AC. So as a result, so now we use electric energy. One of the reasons because you can easily transport it over long distances. So if you try to use thermal energy, yeah, you can transport it maybe from your basement to your house, right? To the rooms, right? To keep your room warm, right? So that's usually the extent of the distances over which thermal energy is transported, right? But over long distances, yeah, it's not very efficient. But electric energy, easily. Right. So that's first reason, because we can transport it into over long distances. Then the second reason. Okay, so now let's say electric energy is in your house. So how do we use that electric energy? Do we use it directly? No. In a few minutes, I will tell you where examples, and actually horrible examples, where we can use electric energy directly. But how do we usually use it in our house? Let's say I want to, I know, warm up my room, right? Let's say it's cold, right? So what do? I take a heater, plug it into the electric outlet, right? And then what does the heater do for me? It transforms electric form of energy into thermal form of energy. So you see, I don't use the electric form of energy directly. I use my transformer, right? Heater is a transformer, right? Or hair dryer. Hair dryer, what does it do for us? Again, you plug it in the outlet, and it transforms electric form of energy in two forms of energies: mechanical, yeah, because it's spinning something, right? And also thermal. Again, it transforms. It's another transformer. Then let's say you want, I don't know, vacuum the floor, right? You take a vacuum cleaner, again, plug it in, and that vacuum cleaner again transforms electric form of energy into mechanical form of energy. Again, you see, we don't use electric form of energy directly. We use our transformers. So basically, if you go to the electric store, buy all these appliances, you buy transformers, right? Then if you want to generate light, you use the bulb, right? And it transforms electric form of energy into light. Then if you want to generate electromagnetic waves, you use a router, right? So again, you plug it into the outlet and it generates electromagnetic waves. You see, every time we transforms electric form of energy into some other forms of energy, right? So we don't use electric forms of energy directly. Let me ask you, where do we actually use electric form of energy directly? Okay, as humans, right? And I can think of only two options, two ways, right? And actually, they're all horrible, right? So, first, doctors can use discharge, I know, to jumpstart the heart. Direct application of electric form of energy, or electric chair, right? Again, as I told you, horrible examples, but that I can think of only these two examples where electric form of energy was used directly. All right. Otherwise, all the time we transforms that. Okay, so now if we transforms all the time electric form of energy into something, into some other forms of energy, then what's the natural question that you should ask? And actually, I'm sure that any human brain will start asking that question. How much of energy are we transforming? Right? How much of electrical energy we transform into, for example, thermal energy, right? Or something else. And actually, physicists usually, and of course engineers, they don't ask how much of energy we're transforming. They're making one step further or deeper, and they ask this question: how much of energy do we transform per unit time? Which quantity are we talking about? Energy per unit time. It's a power, electric power. So that's how naturally we come to the sort of desire to calculate. So what about electric power? Because in all these devices, we transforms all the time electric form of energy into something else. And of course, a natural question: how fast that energy gets transformed? All right. Okay. So now that's sort of the introduction, and now the actually expression which we need to use, or formula which we need to use to calculate this electric power, right? So I'm not going to derive it. Derivation is here. I will just tell you the final result. So let's assume that we have some device. In the simplest possible situation, it can be just a resistor in a circuit. And you know, when you close the switch, current starts flowing through the circuit, you can feel that the resistor gets warm, right? Basically, what happens? So electric energy is transformed into heat. So, and if you want to know how much of energy gets transformed into this heat, yeah, we can use this. Right, so let's say if you have potential difference delta V across an element, current I flows through the element, through this device, right? So then power transformed, electric power, is the product of electric product of the potential difference and the electric current, right? Usually in the Ohm's law, we divide delta V by I. Here, in this formula for the power, we multiply potential difference and the current. So that's how we can calculate electric power, right? Then, of course, we can rewrite this formula in a slightly different way. If you apply Ohm's law, you can write it in two slightly different forms, right? So again, this is just I delta V. And then if you use Ohm's law, you can write this as, for example, if you want to get rid of delta V, you can end up with I squared times R. Sometimes this formula is slightly more useful, not useful, slightly easier to apply than this, right? Or if you want to have formula in terms of delta V and R, so you can write it as delta V squared over R, right? So three forms of this formula. So either I delta V, I squared times R, or delta V squared over R. It depends what is given in the problem. Sometimes this can be easier, sometimes that can be easier, sometimes this can be easier, right? But again, you can use any of these formulas, but if you use not the most convenient, then you will have to make, for example, two steps in order to get to the conclusion after one step, right? So I will be mentioning and discussing which formula is the most convenient for this or that particular case. We will look at a couple of examples. Right? So now let me ask you a question, conceptual question, and the question which I like. I like it. Actually, before I started teaching, I never thought deeply about this. And now let me ask you, and then I will talk. I will tell you what's the story. So here's the situation. We have two bulbs, 60-watt bulb and 120-watt bulb. Here I have one, and yeah, that is a 60-watt bulb, right? Just regular incandescent bulb. I still have two, right? All right, and so we have these two bulbs connected like this, and they are driven by some battery, right, with the potential difference delta V. Delta V is not given, but it can be 120 volts, maybe 220 volts, or maybe some other voltage, but it's powerful enough battery to drive both of these bulbs, and they actually produce light. Both of them produce light, right? So now the question is, which bulb out of these two produces more light? So the question is like, which one glows more brightly? Right? And we have three options: 60 watt, 120 watt, and they have equal brightness. So it means that A, 60-watt bulb produce more light. B, 120-watt bulb produce more light. Okay, give it a try. The question is in the chat as usual, and this question has okay, it's an interesting question. Let me put it this way. So now let me discuss. So first of all, we need to understand, what does 60 watt or 120 watt means. What do we mean by this wattage? Okay, these bulbs, right, are produced and fabricated by companies for the US market, right, for people who live in the US. And so how do we use these bulbs, okay, on the territory of the United States, right? So you take the bulb, put it in the lamp, and lamp goes into the electrical outlet, right? So as a result, what's the potential difference do we usually apply across our bulb? 120 volts, right? 120 volts, that's what we apply. So, of course, the companies producing, fabricating these bulbs, of course, they know that. And in order to make our life a little bit easier, right? In order to make a decision which bulbs to buy, right? Of course, they calculate wattage produced by the bulbs, assuming that 120 volts potential difference is going to be applied across the bulb, right? So as a result, all these numbers, 60 watts, 120 watts, is calculated by the companies, assuming that we use 120 volts potential difference. But if I take, for example, this bulb, I don't know, to Europe, for example, I don't know, to Hungary or Poland or Ukraine, right? These numbers will be almost useless, not completely useless, but almost useless, because there people use 220 volts potential difference. So these numbers are not going to describe the amount of light produced by these bulbs. And again, they're not going to be completely useless, but somewhat useless, because in that case, you will have to recalculate the actual power, right? So the same story in our situation. You see, these bulbs are connected to a battery, and the potential difference we don't know. Even if you pick 120 volts potential difference across this battery, then potential difference across this bulb is not going to be 120 volts, and potential difference across this bulb is not going to be 120 volts, right? So you see, these numbers, 60 watt and 120 volts, do not describe the situation in our circuit, right? So these numbers in this case, again, it's not completely useless, but they don't describe the actual wattage of this bulb in this case, right? So you see the point? So now it means that we need to somehow calculate or get some information about the actual power produced by these bulbs for these particular conditions, right? So in order to do that, yeah, first of all, let me open what I just told you, right? So that companies all the time assume that we use 120 volts potential difference. So now, in order to calculate the actual power produced by the bulbs, I'm thinking that we need to get some information about the truly intrinsic parameter of the bulbs. Because right now we realize that 60 watt and 120 watt, it's an intrinsic parameter only within the territory of United States, or the country where 120 volts potential difference is used. But it's not. But it doesn't happen in our case. So these numbers are not intrinsic. So now let's get information about truly intrinsic parameter of the bulbs. So it doesn't matter where you use these bulbs, I don't know, in US or in Africa or on the moon, right? So that parameter will be still exactly the same for the bulb, for a particular bulb. And I'm thinking, let's get information about resistance of these bulbs, right? Because yeah, it doesn't matter where you use these bulbs, resistance are going to be the same. Because resistance doesn't matter what's the potential difference you apply or what's the current flowing. No, resistance is there, right? So if you fabricated the bulb, resistance is already there. So let's get information about the resistance, and I claim that this is truly intrinsic parameter. So once we get information about the resistance, then we will be able to somehow get information about the actual power produced by these bulbs, right? So let's get, and of course, the resistance we will calculate based on this information, because that's what we have. So companies, which information given by the company. So now, which formula can be used? I mean, formula for the electric power, right? You remember there are three of them. Okay, so we need to get information about resistance. We have information about power, and of course this information about power was calculated using 120 volts potential difference. So we have power, resistance, and potential difference. So it means that the most convenient formula will be delta V squared over R. Okay, let's try to use that formula. So you see, P over 60 watt bulb equals delta V squared divided by R. And again, I'm using these numbers which are given in order to extract information about the resistance, right? So power is 60 watt. And again, as I said, they assume that we use 120 volts potential difference. So as a result, we can calculate resistance over 60 watt bulb, right? So you see here we have 60 watt, and so pretty much we can solve it for R60. Okay, we can solve it for R60. Right, so that will be that number. Okay, you can calculate number. I don't want to calculate, because again, at the end we want to compare powers, right? Which one is produces more light and which produces less light. Okay, so that's the resistance of a 60 watt bulb. Now let's do exactly the same for the second bulb, for 120 watt bulb. So exactly the same idea. So power equals 120 volt divided by the resistance of the second bulb. Okay, so we can solve it for resistance, and now we have this information about resistances, and now we have a truly intrinsic parameter of these bulbs, right? So now we can use these numbers in our actual circuit, right? In this circuit. Okay, and let's compare, of course, which resistance is larger. since 60 watt here is in the denominator, here we have 120 watts. Of course, our resistance of a 60 watt bulb is larger, right? So we can compare now resistances. Okay, so now the next step. Now we have, since we have this intrinsic information, information about the intrinsic parameter, we should be able to get the actual power produced by the bulbs in this particular case. Right. Okay, so now which formula should be used? Again, formula about the power. And I'm thinking about, look, what is given? We have some information about resistances. And look, since these two bulbs are connected in series, what is the same for these two bulbs? Current, the electric current. So current the same, we have information about resistances. It means the most convenient formula is going to be I squared times R now, the most convenient. Okay, so I can use, for example, for the case of a 60 watt bulb. So, and this is power produced by 60 watt bulb, actual power for this particular case, when these two bulbs wired like that. So this is the actual power which we want to get, which we wanted to get at the end. So I squared times R, a resistance over 60 volt. And of course, exactly the same we can write for 120 watt bulb. Again, actual power produced, again, in our case. Okay, so now we have these two powers, and now let's compare which one is larger. Currents are the same, because again, these two bulbs are connected in series. No junction points, so current must be the same. But we also know at the same time, we just found that resistance of a 60 watt bulb is larger than the resistance of a 120 watt bulb. And so as a result, we can say that power, actual power produced by 60 watt bulb is going to be larger than power produced by 120 watt bulb in this particular case, and of course in this situation, right? So you see, in this case, actually, bulb with the less wattage produces more light, actually. Because again, this number, 60 watt and 120 volts, they're calculated assuming that one bulb is going to be across 120 volts. But since in our case, it's not the case, it's not the situation. So you see, we calculated and we got the answer, which is counterintuitive. Not intuitive at all. Okay, so I like this question. It's a very nice question. And again, before I started teaching, I didn't realize this fact that companies calculate power assuming that we use 120 volts potential difference. It's a nice question. I like it, right? It's not trivial completely. And of course, if you didn't understand it at the very beginning, it's normal. Most of people don't realize that.